assume diffusive equilibrium, the upward extension model. So this is maybe not direct. This is to give you direct data point along where the satellite direct data being made, and then compare with the. There are still something will not being captured by the model, but most of the variability and the direct data, I would say, is better. I didn't present with the diffusive equilibrium extension, but it looks like we did a pretty good job in getting most of the variability of the satellite direct data. So, so this is probably give you a better illustration of how the model performs in winter, summer, and spring, or the March equinox. So this is a correlation coefficient. Looks reasonable considering there are a lot of model limitations whatsoever. Okay, so that's about it. So now with the model is fully coupled with the driven by the camera and highlighted the magnetosphere, RCM fully coupled into the major simulated model. So this model is going to be available at the CCMC this year as a run-on request, and then also going to be open source for the community to use next year. That's our plan. So you can just this will be open source to everybody next year. That's our plan and a commitment to do that. So you can just download or do whatever you scientific studies. Lastly, is just to present the SpaceX simulation, the storm simulation. This is the swarm A observation, which is a black line. This measures the density, and this is the MSS here, and the DTM is another empirical model. So we just compare the model, the neutral density on the swarm at altitude at 400 kilometers or so. So this is the percentage change simulated by maze with TIEGCM and DTM and MSS. This is percentage change, so not the absolute density variation. So at the swarm, I present Monday's altitude, so you can see the major simulated density variation. Like this, you have up to 100% density variation along the Starlink satellites, whereas this is predicted by the MSS and the DTM, which is driven by AP. So it's you can early recover from the MSS and the DTM because it's driven by AP. So as well as there's the back, and then back you don't simulate the recover phase and stay the thermosphere continues perturbed or stay there, the inertia there. So overall, that's what I'm presenting. So this model 2.5 is available at the CCMC right now for run-on request. And it's the 2.5 I hope present so we have a better representation of ionosphere structures in the top-sized ionosphere and also at in the equatorial region. And we say we can do a little bit better job in neutral density in the upper atmosphere. And clearly we coupled with camera and to be part of the NASA Drive Center CGS major model. So this is just, we just developed this and over the years, and now it's make it 2.5 as final release. But however, this is a lot of validation need to be done, either to document where the model is doing good, where the model doing bad. Any new physics need to be included in the model or whatever. That's we need community users if you see it, and then feedback, and hope get a better model along down the strand. Okay, thank you. That's all I want to say.
Yeah. So I guess one of the, I'm unclear about like how NCAR is maintaining. Are you maintaining Wacom X and TIEGCM at the same time? And are these like developments then going into Wacom X also? Do you have like compatible code development or something like that?
Thanks, Aaron. Really like this question. First, I would say NCAR only support Wacom X, not support TIEGCM. This is just personal interest, and by individual grant, NCAR not put $1 into this one development. And however, like O+ development, whatever, those are transmitted and still being transferred to Wacom X. So it's Wacom X is NCAR core development task, but TIEGCM is not. So, but because TIEGCM being used widely somehow in the community, so we still, and also for specific purposes, so whatever we develop this, continue to develop TIEGCM, but that's on grant based, not NCAR, not support this effort. Okay, thank you.
Any question? Yep.
Yeah, so just for when the TIEGCM is coupled with GAMERA, does GAMERA also provide the aurora precipitation hemisphere power?
Yes, what I probably not make this clear because time constraint. Here, basically, it's when we fully coupled. This is fully coupled two-way. We are GAMERA and ICM. So with mono precipitation, aurora is from MST calculation, like use that's a relationship, night relationship, and others is use MST code for develop specify the mono precipitation, and use RCM drift physics with do the diffuse
Okay.
the precipitation. Then those are used into TIEGCM and calculate conductance, then feedback to this ionosphere electrodynamic solver to get the potential, and all each to feed back to all those three component models to drive the plasma drift.
Okay.
So that's what it is.
Okay, thanks. And I have another question. So for the standalone, is there any update on the top boundary condition for the heat flux and heat flux?
Yes, actually, we the two top boundary conditions for critical for TIEGCM is one is the O+ the diffusive flux, and another is the heat flux from the also from the plasma sphere. We have the doing those things. Yes, the top side, as we move upward model boundary, we need to modify the O+ diffusive flux as well as the heat flux. Those, that's why I say it's still ongoing work and still validate, just to make sure those are adjusted accordingly. And also, we're still working on that. This is not why we not put on the website and say, okay, this, you can use it, but we still validate those kind of,
Okay.
yeah.
Okay, thanks.
Final
Yes.
question.
So it's really nice to see the progress from 2.0 to 2.5, but it sort of begs the question, what's coming up in 3.0? I mean, it seems like you're capturing the large scale and the larger mesoscale, but the smaller scale phenomenology seems to still be washed out. What are the plans going forward?
Yeah, for this one is, to be honest, for me personally, I really don't have to go to 2.5 for 3.1. I know actually use icon data to drive TIEGCM. That's another lower boundary, maybe another way, another possibility to go with a better lower boundary, either use Wacom X or other data assimilation. Those things that would be one of the paths to move forward. That's nice. And also, clearly, this is TIEGCM right now is in the maze model, but the next step is to replace with Wacom X, so that in this maze model we will to from ground above. So that's another for the CGS development. But TIEGCM itself, I believe, is data assimilation and other data-driven lower boundary will be the next step for to move forward. Yeah.
Okay. Thank you.
Thank you.
Please join me and thank Wenbin again. Our next speaker is Enrique from Cornell University.
Hello, I'm Kike. I'm a postdoc at Cornell, and I'm going to talk about a couple of projects that we're working with some Peruvian students and with Marco Milla as well. So this is going to be an overview of these couple of projects. We are doing machine learning modeling of electron densities and spread of occurrence. So first, an introduction, then an overview of the two projects, and finally a summary and conclusions. So as you know, space physics is full of nonlinear phenomena, very difficult to capture, even with very sophisticated models, and there is a lot of impacts on technology, but nowadays we have, I think, enough data to have the luxury of building empirical models, statistical-based models that can learn these variabilities, this correlation between inputs and outputs. And in this work, we're going to present two types of neural networks. One is a regression neural network, and the other one is a classification neural network. So first, the first project to predicting ionograms. So the motivation for this study was to try to build a system that can learn to produce electron densities with geophysical parameters. And unfortunately, we don't have a lot of electron densities, but we have a lot of ionograms. And this work was done with Jasmine Aricoche. So the mathematical problem can be stated as follows. We know that there must be a function that goes from X, geophysical parameters, to Y, electron densities. And the neural networks are very good to reconstruct any functions if you have good mappings between X and Y. But unfortunately, we don't have Y, we have G of Y. So instead of, we're going to postpone this electron density learning for later, and in this project we focus on trying to capture and trying to teach this neural network to predict ionograms only, which should be an intermediate step as far as I know. So the time series that go into the input of this first neural network, they look like this, the regular geophysical parameters. These are transformed time series of time in sine and cosine components. And these go into the first neural network, a regression neural network that predicts the actual virtual heights. But as you know, these virtual heights, they need a cutoff corresponding to the critical frequency. So we have a second neural network embedded on this one that cuts that estimate the critical frequency and cuts the predicted ionogram. So this is the training strategy that we developed. It was basically like a rolling window. We took 3 months of data and 1 month of data. We used 2 different strategies. And we trained with the first 90% of days, then used 10%, the following 10% of days to, random 10% of days within the training data to find the optimal hyperparameters, and finally do the prediction and compare with the actual values. So these are examples of what we get. In the first row, we have here for morning ionograms and here for afternoon ionograms. And you can see here the black dots correspond to the DigiSon values, and the blue dots with the neural network with 1 month of training, and the pink ones with 3 months of training. And you see they are pretty similar to the data. And then here in the second row, corresponding to the same hours, we are comparing this with SAMI2 estimations, with ionograms obtained from SAMI2 estimations and ionograms obtained from IRI estimations. And we see that often our neural network predicts ionograms better than these other models. Okay, So this is just error bars of the actual estimations of the virtual heights that we get from different models. So the first row corresponds to the neural network with 1 month of data, and the second one with 3 months of data. This is for morning and afternoon. We see that, of course, there is more errors corresponding to closer to the critical frequency in both cases. And also we see that increasing 2 months of data, it really is not critical for the model to capture the variability. And we suspect that this is because of the periodicities that are hidden in the time series. This is a summary of some tests that we have done so far. We compared it with December 2009, March 2009, and so on, which we think were representative solstice equinoxes. These are the RMS errors of the virtual heights for these two different models. These two columns correspond to the 1 month neural network, 3 month neural network, and this is IRI and SEMI2. So the lower the value, the better the model. You can see that the errors even with 1 month of data, they are pretty good compared to the other models. So I finished this project with a couple of open questions. First, what is the best strategy to modify this architecture to teach the neural network to predict electron densities instead and not ionograms? We think that it's we have to tweak and hack the loss function of the neural network, but there must be an optimal way to do it. And then, what is the optimal architecture for this model? We have already started exploring this question, basically doing a lot of hyperparameter optimizations. There are special tools for that. I can talk about that later if you want. So now I'm going to talk briefly about the second project, predicting occurrence of spread F. So as you know, spread F is usually related to this generalized Rayleigh-Taylor instability. That's one way to call it. So if you have gravity, background magnetic field, and you have a steep difference in the density of the plasma, any perturbation is going to be enhanced in this way, following the regular theory. And if you point a coherent backscatter radar to space, like in Hicomarca, you're going to see these Doppler signatures of these structures, 3-meter structures. So this project, we work on this project with Reynaldo, who won the poster competition as an undergrad. And okay, so in order to build a model neural network, we need X and Y. X is going to be probably some set of geophysical parameters, and Y in this case have to be occurrence data, occurrence of spread F. So what we did was, what we did was to take the Julia radar and define some criteria and propose some criteria to define occurrence of spread F. We were based on Sun 2008 paper to do this. So this is more or less the data that you can get from Julia. These are this is backscatter power, where the turbulence is stronger, more coherent, so there's more power scattered back to the radar. So we defined some criteria. We resampled the RTI and put a threshold value for the SNR. And we said that, for example, if this is yellow, then there was a spread F. If it's black, there was not. And then we collapsed this to 1 dimension in time. So we know that at 7, for example, there was no spread F, but here there was, and there was not here. So now we have our occurrence data, our Y set. Then these are the geophysical parameters that we decided to include. And the main difference with respect to the ionogram project is that we are including H prime, because it has been noted that H prime is related to this upwelling condition, which is a good predictor of occurrence of spread F. And we also included some operations on H prime, like the difference between the consecutive H prime and things like that, to see whether the neural network thought it was an important parameter. So after doing hyperparameter optimization of the structure of the network, we came up with this architecture. It has a very common structure, like several neurons, several layers, this CELU activation function, dropout to regularize to avoid overfitting. And the training strategy was this one, 70% training, 20% validation, and 10% testing. So in order to have some reference, like in the case for ionogram predictions, we chose this first model, which is a model that works as follows. They start with the assumption, it's a model for predicting spread F as well. They start from the assumption that there is an electric drift and E cross B threshold for high scintillations. Then that E cross B is well correlated, that the vertical drifts are well correlated with H prime. And therefore, if you assume these two things, then you have to assume that there must be some threshold in H prime that can be used to predict high scintillations. And if you do that, you can relate this scintillation occurrence with the spread F occurrence. And they did that, and they got very good results when the occurrence data was built with ionograms, local ionograms. So we use this model, but now we compare it with, we use it when the occurrence data is defined by Julia and not by an ionosound. So we got these results. This is the map of this confusion matrix, and this is what we call confusion calendar. And the accuracy that we got with the first model is 73%, which is pretty good. And our model got an accuracy of 81%. And yes, this is true positive, this is true negative, and so on. And then we did sensitivity analysis using Chou values, which is very useful. So the way that you interpret this is as follows. The color indicates the value of normalized value of each of these parameters. And the more to the right you are, the better the predictor of occurrence it is. So this means that, for example, the cosine component of the time series is an extremely good predictor of occurrence of spread F if its value is high, and the opposite if the value is low. Or for example, if H prime, if you want H prime to be a good predictor of spread F, it needs to have a very large value. And something similar happened with AP. AP, for most of the values, is not a good predictor, but when the values of AP are very high, it is a good predictor. And there was a poster that actually got the same results here with different techniques. So I leave with a couple of open questions. Like, for example, how to understand the differences between scintillation occurrence and Julia occurrence, and for that case, ionosound occurrence of spread F. And yeah. Now the summary and conclusions. So the regression neural network for the ionogram seems to be very promising. We are getting better results than SAMI2 and IRI at least. And the classification neural network to predict spread F occurrence seems to be outperforming the first model, which is based on a linear regression model. Some future work that we're working on right now is, for example, maybe we can tweak the input parameters to build proxies that can capture better, for example, the growth rate of spread F. Maybe combining geophysical parameters can correlate better with growth rates. Then we're working on teaching these neural networks to learn electron density prediction, and we are particularly interested in the possibility of predicting spread F RTIs, treat them like with convolutional neural networks or like image prediction. So yeah, that's it. And if you have more questions or want to write me, you can, this is my email, so thank you.
Thank you.
So I have 2 questions. The first one is how long can you do the prediction and whether the errors will increase when you go to the longer prediction? The second question is to what extent your prediction depends on external drivers? I don't know, you said you have inputs to the model. So what is the dependence on that? Thank you.
Are you asking about the prediction of ionograms or spread F?
Either one.
Okay. So the prediction of ionogram, we see that the predictions degrade. So it depends how we train them. We have trained a neural network, a climatology prediction of ionograms. That climatology model doesn't degrade very fast. So you can make 1-day predictions, 5-day predictions, but it's not significantly better than empirical models and numerical models. But when we train the neural network with like this amount of days and then make the prediction of the immediate following days, then that's pretty good and it's better than the empirical and numerical models. And but it degrades after maybe 5 hours, something like that. And spread-F, we haven't really assessed how rapid it degrades because we did, in order to compare with the first model, we used the first model rules. And what they did was to see the value of H prime at 7:30 p.m. and make a prediction of occurrence at 9:30 p.m. And we did the same. So that's the only information we have so far about how the spread-F degrades. But it would be, I think, very easy to extend the model to make predictions for the rest of the night because we have the time series for that already. We just focus on those hours because those were the hours where the first model was built to make predictions to. Mm-hmm.
So I have 2 questions about your ionogram model. So the first is, I might have missed it, but are you using scaled data or are you using the raw ionograms and then doing some sort of pre-processing before you're fitting?
Oh, we are using ionograms straight from the DigiSonde.
Yeah, but so the actual raw amplitudes
or
the scaled parameter, like the scaled virtual light profile?
Okay. So the DigiSonde gives you. I'm not even sure if you can access the power, the power for each beam. What we use is the scale version, so that whatever the DigiSonde scaled to us. Yeah.
So the auto-scaled data then.
Auto-scaled virtual height curves. Yeah.
Right. Because the autoscaler is kind of a combination of image processing and neural networks itself, and so it implicitly has its own biases in how it sees ionograms.
Yeah.
I'm just wondering how that might affect, like, how close, like, if you compare it to manually processed data, how does this actually perform?
I don't know if I can say anything about that. We haven't. We are assuming that the models that they have, they're pretty good when the classification flags are good. So, so these are the classification flags for the ionograms, and we just focus on the best ones. And there must be biases in going in the identification of the traces. I agree, but I would say that the main, maybe for us, the main metric for success was the comparison with other alternatives, and we are not. I don't think we are too ambitious to try to get the correct ionogram. We just want to outperform the other options. Yeah.
Right. Well, so the fact that you actually have the 2-character classification levels there means that it's artiste 4 rather than artiste 5. So it's an old version of the software as well, which can have problems. But anyway, I'll send you a paper if you'd like that kind of goes over how well these actually classify how ionograms perform.
Okay.
I'll ask my second question later. Thanks.
Okay.
Please join me and thank Enrique again. Thanks. Our next speaker is Jasun from Yonsei University, right? Yeah.
Okay, so today, today I show some result from quantitative assessment of coupled ionosphere-thermosphere models for TEC and FF2 prediction. So actually this study is an extension of our previous study to track the model improvement, also to investigate impact of higher and lower boundary forcing on model performance. So we used two simulations from CTB, one from older version with tidal mode, and the other is with new version with tide from WEM models. And also we use two simulations from GTM, one from older version with ovation auroral precipitation, and the other is updated one with FANG's auroral precipitation. Also, we use TIEGCM to compare with two simulations of WACOM-X because WACOM-X, TIEGCM is implemented in the WACOM-X. So two simulations from WACOM-X is one with Hillis and the other is with Weimer. So Chou provided this simulation. So as you can see here, there is a difference in altitude range for TC calculation. So only CTB includes plasma sphere and the other models don't. So we made these models run for 2013 March storm event, which is one of the most famous March event. And so to quantify the storm impact, we use 30-day median value as a quiet time reference. So we made a comparison between model and observed value for this selected 12 location, 4 from North America and 4 from European sector and 4 from Southern Hemisphere in order to see the longitude dependence and also hemispheric dependence on model performance. And observed value used FOF data from GIRO and also GPS TC data from MIT HASDM Observatory. Okay, this is the observed FOF to TC during the main phase at 12 locations. So we only focused on the main phase. So we found storminess density in European sector and also Millstone Hill around 12 UT and 20 UT respectively. And also negative storm is observed in west side in North America sector. So most cases in FOF and TC show similar change with larger change in TC. However, if you see these two locations, and we have huge TC increase, but there is not much in FOF2. Okay, so for quantitative assessment, we use 4 different quantities shown here. Shifted TC and TC difference compared to quiet time and also percentage change and normalized percentage change. So by using these 4 quantities, we can remove the baseline and also to reduce difference in upper boundaries, as I mentioned earlier. So actually, we used this normalized percentage change because it has a kind of advantage to exclude local time and seasonal and latitudinal dependence, so only include mainly storm-induced variations. So for quantitative assessment, we calculate several skill scores, correlation coefficient, root mean square error. Also, we include a ratio of peaks, model to observed value, and also timing error, the difference between the measured and observed peak time. So we calculate these 2 values in these 2 time interval, 6 to 15 and 15 to 22 UT. Okay, this slide shows scatter plot between modeled value and observed value for CTB and old one and new version, and GTM for old version with new version. So as you can see here, old CTB is kind of underestimate FOF and TC, and new version is kind of overestimate and TC, especially in North America and the South Africa sector. And it's all two GTM simulation shows kind of similar behavior, but higher value of TC in South Africa from this new version better correlated with observed GPS TC. Okay, this one is actually same as previous one, but for TIEGCM and WACOM-X3 with Hillis and WACOM-X with Weimer. So three simulation kind of show similar tendency, and also these three simulations tend to underestimate FOF TC in this red dot is for South Africa. Okay, different colors indicate from different location. So also TIEGCM overestimate TC in North America and WACOM-X in South America. Okay, so here is correlation coefficient for FOF2 and FOF2 change and also percentage change. Here is TC with a normalized percentage change. Here, for each simulation, first dot is average value for over European sector. Second one is average over North America. And the third one is for Southern Hemisphere. And last dot shows the average for these three all location. And if that, so if that is kind of going up or and down, and that means model performance highly depends on the location. So average correlation coefficient for this FOF2 and TC range from 0.8 to 0.95. And CTB is updated version kind of show better performance in these quantities. And also GTM updated version show better performance in this location and also these quantities. And WACOM-X simulation show better correlation coefficient than TIEGCM. So most simulation show lower correlation coefficient in North America sector. I guess this is because model kind of failed to catch this opposite response to the storm, the negative in west side and positive in east side. Okay, this is the root mean square error for FOF2 and the change in FOF2 and also the TC. So average root mean square error for FOF2 is range from 1.2 and to 2 megahertz, and for TC in 5 tech unit and to 10 tech unit. So new version of CTB has smaller root mean square error than the old version, and also the new version of GTM showed us better performance, especially in Southern Hemisphere than the older version. And comparing these three, two WACOM-X and TIEGCM is WACOM-X with Weimer show better performance than others in terms of root mean square error. And root mean square error varies highly with the location, especially in larger root mean square error in South Atlantic anomaly region. I think it's because of the model don't have this energy input from the radiation belt. So if we use kind of new updated like maze output, probably will catch this enhancement in this region. Okay, this is a percentage change, root mean square for predicting percentage change. So, yeah, it's same as before. Previous one is model perform very highly, varies very highly with the location. So if you compare this, I only focus on the average value, and so the lower value is the better performance, and the new one is new CTB has small root mean square than old version, and here WACOM-X, for WACOM-X with Weimer has show a better performance than these two simulations. Actually, but for this average root mean square for percent change in TC, actually old version of CTB show better than the new one, and also TIEGCM show better performance than these two WACOM-X. And normalized percentage change of TEC, and here again the old version of CTB, but here in WACOM-X with Weimer is better. And for all quantities and new version of GTM kind of produce better root mean square error for these quantities. Yeah, same here in larger root mean square in Southern Hemisphere than European sector and North American sector. Okay. Oh. It doesn't go back. Okay, I'll just show. So previous slide shows a kind of ratio of, oh, okay, I have this. Okay, so this one considered 2 time interval, as I mentioned earlier, is 2 time interval. We only consider the positive yields. That means if model meets this, the phase, and then we exclude that, the result. So we only include when the model is predict this phase correctly. So old version of CTB is kind of underestimated, so this yield is less than 1. And this, for this quantity in the old and this new version is close to 1. And also here for GTM, new version is kind of better for this percentage change in terms of yield. And also TIEGCM is closer to 1 than the WACOM-X. Okay, this is timing error. So the smaller value is the better the model performed. Okay, so new version is better for CTB, and also GTM is new version better. And here for this FOF percent change, TIEGCM is a little bit better than WACOM-X, and the other here average timing error of this percent change in TC and old version is a little bit better and new version. Okay, so average timing error for this one is kind of range from 1 to 2 in these all cases. This table shows the total number of locations where the models predict the storm phase correctly. So if we compare these two, and old version is better for FOF2, and the new version is better for percentage change, and GTM show better for these 3 cases, and old version is better for this percentage change. And TIEGCM and WACOM-X, WACOM-X 4 is better for FOF2, and TIEGCM and WACOM-X 3 is better for percentage change to catch this phase, storm phase. Okay, this is my last slide to summarize. So basically, basically everything is what I already said, and then just point out. I hope I can say updated version of model show the improvements, and there is no one best simulation for all location and all metrics used. It all depends on. Okay, so that's it.
Thank you. Any questions? Aaron?
So one of the things that weather forecasters do is put together all of the models together to make an ensemble.
Yeah, sure.
Have you thought about just averaging all of the model results together to see whether that actually beats all the models?
Oh, actually, we kind of discussed about that, but we never tried. But I think it's a good idea. Yeah, yeah, sure.
Okay, thank you.
Thank you.
And our next speaker is Mingyang Zhou from NASA.
Hello, I'm Min Yang from CCMC. So this room is really big, so it takes me some time. Yeah, okay, so today my topic, I'll talk about the assessment of ionosphere models during the geomagnetic storm time in low and moderate solar flux years. So this study is contributed by Jia Yue, Jack Wang, Masha, and Joe Huba, and also thanks Zhu Wei and Dom provide me the service models like GORTEC and the CTIP and one IPE. So first talk about the ionosphere models and observation we use to validate the CCMC model. So first I will use the ground-based GNSS observations from Madrigal, TEC, MIT. So he provides a global coverage of ground-based GNSS observations. And I also use the spaceborne RT observations from the Formosa 7 cosmic Chou. So it can provide FOF2 and M2, so we can evaluate the performance of model regarding the TEC and FOF2 and HF2. So because of the data coverage of cosmic Chou, because it only focus on the equatorial ionosphere, so we only focus on the equatorial ionosphere around the magnetic is around plus minus 45 degrees. Here's all the models we use for validation that we have GORTEC provided by Dom flew well. And the III 2016 SEMI-3 is a new version of SEMI-3. We recently updated to 3.22. And the GeoHuba also provides the SEMI-3 RCM, so it hopes that it can show better performance during the storm time. And the Zhu Wei provides the 1IPE CTIP E 4.10 version. And now we will onboard WakeUp as he is recently. I think maybe this summer we will have this model on board CNC for run request. And we also have new TIEGCM model 2.0 Weimers here. And yes, in this talk I will only cover these models, but in the future I will include like Gitten, SWF, MF, PBMA provided by John Ritter, and also we will have this PBMA on board CCMC soon, I think this summer. And also I will include the global ionospheric specification as a data assimilation model provided by TACC from Taiwan. So talk about, so this study will focus on the two storm case in 2013 and 2021, because I choose this case because now is a solar minima time, so we don't have much storm, I choose this because it shows they have more cosmic Chou data coverage. And also you can see that the DST index here shows a very similar value. And also the KP index also very similar. So I think it's both two cases should be very good example for model comparison, except that F10.7 is different. So here's the matrix and the skill score we used to evaluate the model performance. So here there are three categories of the matrices I use to validate the model. First, I will evaluate the accuracy of the ionosphere models using the mean absolute error, median absolute error, and a root square error. The second is the precision. I use the standard deviation to evaluate the accuracy, the precision of the model, and also lastly is the correlation coefficient. And the skill score is based on the Lim Hum et al. 2021 JSTP paper that he tried to calculate the skill score based on the matrix. So we have the skill score equals matrix new subtract matrix reference divided by matrix perfect subtract matrix reference. The matrix new indicate the model we use to validate, so we can calculate the skill score. The matrix reference indicates the reference model we choose. Basically, you can choose any model you want as a reference, but in this case, we choose IRI 2016 because it shows more stable ionosphere variations during the solar minimum and solar maximum period. So we choose this as a reference. And the matrix perfect means the perfect matrix score. For example, if you choose the correlation coefficient, that the perfect score will be 1. So you can use this number into this equation. So you can compare these models with IRI, so we can know which model basically shows the best performance in comparison with other models. So here just shows that if the skill score is smaller than 0, that means that the model is skillful, less skillful than a reference IRI model. If the skill score is 0, that means it's the same as the reference model. And if the skill score is greater than 0, that means it performs better than the reference model. And if the skill score is 1, that means the model shows very good performance in predicting the ionosphere state. So here first I shows the TEC result. This case is a 2013 March stone case, total content. So here you can see there are like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 models here. 9 models and 1 observations from Madrigal TEC. So you can see 3 consecutive days. Here shows the TEC maps as a function of local time and the magnetic latitude. So you can see the first day shows the quiet day, and the second day shows the stone day, the main phase, and the last day shows the recovery phase. So you can see that the Madrigal TC shows very significant TC enhancement. And you can compare the Madrigal TC, the ground-based GNSS TC, with other ionosphere models. So you can roughly see that which model shows a better performance. So you can, it's obvious that it seems likely that the GeoTech and the II model is just very good performance because it shows very similar structure. And it should be mentioned that almost all of the ionosphere models, they do show very significant enhancement during the stone time. And it also should mention that you can find that the GeoTech symmetry RCM 1 IP and the CT, they tend to be greater than the Madrigal TEC. And ours model like IRI 2016, symmetry, WCAMS, and TIEGCM, Weimer's and Helios, they tend to be smaller than the observations. So here just shows the overall statistic results, shows the difference between the model and the observations. You can see that most of the models actually are quite close to, the median is quite close to 0. That means the difference is very small, except you can see the CT shows it's overestimated. And also the WCAMS and TIEGCM is slightly smaller than the observations during the 2013 March storm. And this another storm time in 2021 November storm, you can see the total storm content observations that you can see the second day you also show very significant TC enhancement, and the third day. So if you compare with other observations, it's obvious that it seems like the TIEGCM significantly underestimates the TC value, also symmetry also underestimate. But if we compare with the symmetry RCM, you can see that it shows slightly enhancement during the storm time. This demonstrates that the symmetry RCM should have provide some improvement. So, okay, if you check the overall statistics result, you can see that the most of the models, they are quite close to, the median value quite close to 0. It said that the TIEGCM, value is too small compared with observations. And overall, you also can find that the GROTEC and the IRI shows relatively accurate results compared with the GNSS Madrigal TC observations. Sorry, I forgot to mention that the GROTEC is a data assimilated model that they use the IRI as a background to assimilate the ground-based GNSS TC and also the cosmic observations. So, of course, this shows the best performance compared with observations. And so we calculate the skill score to evaluate that which models shows the best performance during the solar minima and moderate solar fast years. So here shows the left shows the 2013 storm time and the 2021 storm time. So you can see that the number means the order, which one shows the best performance. So the first that regarding the TEC, the GROTEC shows the best performance. Second is the IRI 2016 model. And if we just focus on the physics-based model, you can see that Wacom X and the symmetry RCM have the better performance in 2016 and 2021 respectively. So, and the CTIP and the TIEGCM shows already bad performance in 2013 and 2021. Next, we compare the FLA2. So here shows the observations from the cosmic FLA2. So it shows very sparse observations during this time, but you can roughly see that actually the quantities between the observations and the models are really comparable, except that the CTIP E shows relatively large values compared with other models and observations. So here shows the statistic result that most models, they are quite close to the cosmic observations, except that CTIP is significantly overestimated. And here shows the next solar minimum years. So you can see the cosmic Chou provides more dense coverage. So you can clearly see the EI structures. You can see the second day that the FOF2 and are significantly enhanced compared with the quiet time. So again, you can see that all of the models shows relatively similar results, except that the TIEGCM that it shows relative the performance is not good during the solar minimum years. So here shows the median value, and you can see that the GROTEC also shows the best performance. And also we calculate the skill score again that you can see the top 1 and top 2 is IRI and GROTEC and IRI again. So, and for the physics-based model, we think that the Wacom X performs better in 2016. And the symmetry RCM performs better in 2021. So yeah, as I mentioned, that you can see the skill score of TIEGCM compared with the 2013. You can see the skill score is significantly decreased compared with the moderate solar fast years. And also, if we focus on the symmetry RCM and the symmetry, you can see that during it also shows better performance during the moderate solar fast years. And so it seems like most models shows worse result during the solar minimum years compared with the models during the moderate solar fast years. And next, we evaluate the ionosphere layer HNF2. So again, you can see it seems likely that most compared with TC and FOF2, you can see the variation is significantly larger than the previous parameters. And you can see that the 1IP, in this case, we find that the 1IP overestimates the HNF2 and the CTIP underestimates the HNF2 compared with COSMIC 2 observations. But all our models, they shows very quite good results, and the quantity actually is comparable to the COSMIC observations during this time. Next is the 2021 November stone. Okay, again, you can see the GROTEC and IRI, this shows very good results compared with COSMIC 2, except that the GROTEC, you can see the EI structure is very comparable to the COSMIC 2, but during the nighttime and the high latitude, it shows that the quantity is slightly overestimated. And we also find that the 1IP here, the value is too large compared with COSMIC 2, and the TIEGCM here it shows the value is too small compared with COSMIC 2. So here shows the statistics result. So again, I would think that the GROTEC and IRI and also Wacom mass here seems like it shows better result in comparison with other models. So here shows the scale score again that regarding the HNF2 that we found that during the solar moderate solar flux years, we found that the Wacom mass shows relatively good results, and compared with GROTEC, IRI, and semi-3 RCM. And during the November storm in 2021, you can see that the IRI shows better performance than the shows the best performance. And for the phase-based model, I think Wacom mass shows better performance during the solar minima storm time. So in summary, that I think we evaluate the model performance during the storm time. So overall, that we find that GROTEC shows the best performance in modeling the TEC and the FOF2 in both low and moderate solar flux years. And the IRI shows the best performance in modeling the HNF2 in both low and moderate solar flux years. So for the physics-based models, I think the Wacom mass and the semi-3 RCM have better performance than other physics-based model. So as I mentioned, that the physics-based model shows better performance during the moderate solar flux years, except CTIP, because the error becomes smaller during the solar flux years. So also, I also noticed that all the models tend to have larger errors during the storm time. So in the future, that we would like to include these models for evaluation. So thanks.
Any questions? Nick.
What were the F10.7 values we used during that 2013 and 2021 storm cases?
Yes.
I guess like how solar minimum, what were those cases like for the?
I choose two cases for.
I guess like what were the F10.7 during those times?
Okay, you can see that the F10.7 is for the 2013 is 132, and for the 2021 case is around like 92.
Thanks.
So the physics models, they don't cover the whole ionosphere. So how's that fold into your TEC validation against like IRI, which covers the whole ionosphere?
Mm-hmm. I think the physics-based, some physics-based models don't cover the whole atmosphere, so that may be one reason that why they show worse performance during the solar minimum years. So it seems like the models can perform better during the solar maximum years because during the solar maximum year, the solar forcing and geomagnetic forcing is the dominant, and it's responsible for ionosphere variability. So if we include the whole atmospheric model, for example, the Wacom mass, if coupled with the semi-3, probably it can show better performance during the solar minimum years.
We need to move on. Our next speaker is David from University of Birmingham.
Yeah, forward, backward, right. Yeah, hi. I guess I'm going to be talking more to my screen than you guys, but I guess there's one down there. No, it's fine. Anyway, so I'll be talking about the validation of the Assimilation Canadian Hierarchical Ionospheric Model, or A-CHAIM. It's kind of a continuation of a presentation that I gave yesterday, so I won't be talking too much about the actual system itself. So I'll start off with really brief on the background model and the assimilation scheme before getting into some test scenarios and longer-term validations that we've been conducting of this near real-time operational high-latitude data assimilation system. So A-CHAIM, or the Empirical Canadian Hierarchical Ionospheric Model, is the background model for this data assimilation system. It covers everywhere above 50 degrees geomagnetic latitude. And it was designed effectively as, it's an empirical model that was designed to replace the use of the IRI at high latitudes. And more specifically, it's designed with kind of HF propagation and kind of applications in mind. A-CHAIM is a data assimilation system based on E-CHAIM that's meant to get us smaller temporal and spatial scales and to debias some of the behavior of E-CHAIM at lower latitudes. This system is a near real-time operational data assimilation system that's designed to support defense over-the-horizon radar and HF propagation applications, so aviation. The system uses a particle filter and a parameterized state space, so we use the same functions as the background model to actually specify our state space when doing the data assimilation, which allows us to do some interesting little tricks to play around with the distribution of information with our state. The system itself actually at every hour goes back 3 hours and then assimilates forward or goes forward 5 hours. So we have 3 hours of effectively near real-time reanalysis, and then we have about 2 hours of persistence rotational forecast. Nothing fancy, just something, I guess, a little bit to fill the gap due to the processing time of the system. What this means is that we actually have 5 different realizations of the state for every run. So for any given point in time, we have a 2 hour or 2 to 3 hour hindcast, a 1 to 2 hour hindcast, a 0 to 1 hour hindcast, reanalysis. And then we have a 0 to 1 hour forecast, and then a 1 to 2 hour forecast. Of course, when we're talking about operational systems, data, or particularly data assimilation, you have to deal with the fact that your data is, diminishing returns as we get closer to real time. So, for example, GNSS data, you're losing data exponentially as you go from 3 hours in the past to the present time. In this case, dropping by an order of magnitude between each of the hours going forward. Ionosphere data is generally available within a few minutes, so that's not really a big problem. We have relatively consistent availability of that data set throughout or regardless of our lags in our data assimilation. Of course, we also assimilate altimeter data, but those are really just kind of a fortuitous orbit once in a while that hits our 2 to 3 hour reanalysis. So this is just an example of the distribution of the ionosomes, GNSS, and altimetry data that's included in the system. Of course, this is over several days. This isn't one period, so that'd be crazy. Red here are ionosomes that are assimilated, so these are available near real time. And these blue ones are ones I'll be talking about today in terms of our validation, which aren't available in real time, and so they present us a good opportunity for doing independent validation of data not assimilated into the state. And you can see, Svalbard is far away from other data, Pond Inlet less so, but there's only one ionosome in the polar cap. And in general, we have data sparsity over Canada, virtually nothing over Greenland, and a huge data gap over Russia. So if we're going to talk about the validation of a data assimilation system, everything really has to be kind of framed in terms of the background model. And in order to kind of understand the performance of the assimilation system, we need to understand the performance of the background model. So ultimately, the A-CHAIM within the polar cap and upper part of the auroral oval performs roughly at the measurement precision level. As we tend to lower latitudes, so subaurora and mid-latitudes, the system generally has performance that converges to that of the IRI, and so the dominant kind of error budget of the system is at these mid and low latitudes. So that's where we expect to have the largest improvements with the data assimilation system, but also high latitudes have smaller temporal and spatial scales, which are what we'd like to get out of the system as well. So, right. So just to talk about some kind of principles that I like to adhere to when doing these validations. I do a lot of model validation in general. And since this was a session that was kind of devoted to that, I figured I'd talk about it. So one, when you validate, well, particularly operational models in general, or data assimilation anyway, you don't validate against things you obviously included in the data assimilation system. That'd be crazy. But also, ideally, you don't validate against things that resemble what you assimilated either. So for example, if you're assimilating total electron content, you don't want to validate against total electron content because that tells you nothing about how that information is being communicated by the data assimilation system throughout the state. A tech map can get you total electron content well. You don't need an advanced data assimilation system for that. What you want the data assimilation system to do is to distribute that information in such a way to get you information about the top side, NMF2, HMF2, the structure of the ionosphere. And so generally we like to avoid doing validations against things that we've directly assimilated. Obviously, operational system performance is fundamentally different from what you get when you're talking about, reanalysis and things of that order. There's data processing errors, particularly when you're talking about GNSS data, for example, that are substantially larger when you're talking real time. You also have, the luxury in Hindcast to manually process ionosphere data, for example. On top of that, even the background model that you're using to assimilate into, it has drivers, and those may not be available in real time. And so some assumptions or some additional error comes just from the background model itself. Right, so, and particularly because this is an operational system that's designed for space weather or applications, one of the things that's be kind of nice, which I'm not going to actually talk about today, so I don't know why I put this in here, but is to validate these systems, not just against things that'll communicate information about how the system is behaving overall, but to also conduct validation in terms of metrics that are relevant to the user. This is a system designed for OTHR propagation, or to facilitate OTHR. So, ideally, we would conduct validation of HF propagation sources, so things like SuperDARN or other HF propagation-based metrics. So, I'm just going to jump right into some of our more conventional validations. So here we have FOF2 from Pond Inlet, Svalbard, Sedunculus, so this is in Northern Europe. This is, I think I pointed these two out there in the polar cap, and Cusp. And then Blissville, which is on the eastern coast of North America. So if you start down at the places where we have lots of data in the European sector and North America, you can see the red is the data, the black is A-CHAIM, or the background model, as it was run at that time. And then blue through yellow are the various different realizations of the state, so going from hindcast to forecast. And you can generally see, at these low latitudes where we have lots of data, the system does a really good job at debiasing the background model and recovering the diurnal variability of the FOF2 at those locations. And if you remove the background model and look at the anomalies, you can see that we're also capturing these smaller scale variabilities that we see in the data as well. Going into the polar cap, where we have substantially less data available, Svalbard, there's only one GNSS receiver near this thing, and so it effectively gets very little improvement. It's the particle filter just decides that it doesn't have enough information to communicate or to be able to distribute the information within the state effectively, and so it says, nope, we're just going to leave things on the background. At Pond Inlet, we have a little bit more data around. We have a few more GNSS receivers, and so we're able to recover some of the variability on those at that location as well. But also, the background model is doing considerably better at these latitudes as well, so it's harder to make improvement. We can look at HMF2 as well. So again, you look at low or mid latitudes, and you can see we're debiasing, which is great. And the most interesting thing here is actually at Svalbard. So Svalbard, again, there's There's no ionosphere nearby. There's only one GNSS receiver. And despite that, we're actually getting considerable improvement in the HMF2 at this location. And that ultimately comes from our basis set being global and the fact that HMF2 actually has relatively large correlation length scales at high latitudes. So we're actually able to communicate information about the height of the ionosphere from middle latitude, or well, auroral latitudes in Europe to Svalbard to actually get considerable improvement at that location, despite having no data. At Pond Inlet, we also see, again, mostly debiasing, but you can see the variability in the height of the ionosphere when you start getting into the center of the polar cap is huge. And so just the nimbleness of the data assimilation system, particularly when it's data sparse, is just insufficient to be able to resolve those timescales and that degree of variability. It looks like noise, but this is actual variability. This is just a summary of that performance. You can see the percent improvements versus the various different lags. In general, for HMF2, we have systematic improvement everywhere. Life is good. Negative is improvement by the assimilation system, by the way. And you can see kind of this general cascade of performance improvement decreasing as we tend into the forecast. For FOF2 at Pond Inlet, where we have lots of GNSS data around, we're able to get systematic improvement, which is good, but not particularly large. At Svalbard, we see much of nothing, about the same. It's just kind of gone back to the background, which is actually good behavior. We want the system to not do anything if it doesn't know how to handle that, particularly when our state space is global and you can have the potential for the system to just start throwing up weird behaviors in places where it doesn't have data. And so we're happy that we've actually stamped out all of that and it's actually behaving very nicely. And then you go to mid-latitudes and you can see huge improvements in the performance of the system because we have lots of data to work with. Of course, that kind of violated my thing where I said I didn't want to do validation against things that resemble what we assimilate. And it's also, we want to validate in places where we had no data at all to ensure that, again, because our basis set is global, that we're not doing weird things in places where we don't have data. So what we've done is we've also looked at DMSP. So these are the RMS errors from the background model, from the assimilation, and then the difference, where blue means improvement. And in general, you can see that we've decreased the RMS at all locations, except for you can see these kind of little blots of red here and there within the polar cap, which have to do with the system deciding that it can't resolve certain spatial scales. And so it's smoothed them out a little bit, and that's why we end up getting a little bit of error there. But ultimately, in places where we don't have much data, Russia, the oceans, we're still getting lots of improvement over the oceans. And that's actually because the propagation of information from Europe is being rotated over the oceans, and that's filling it in, so we don't actually have a significant loss in that region where we don't have any data at all. These are just the overall statistics of that. Again, systematic, 25 to 30% improvement in the hindcast of the reanalysis, and then about 10% improvement even in our 1 to 2 hour forecast. Of course, that's just during a case study. So this is the same thing from DMSP, so at 830 kilometers, but for the entire time that the system's actually been operating. And you can see systematic improvement everywhere. Life is good. You can see, we don't get too much improvement in the rural oval where you have soft precipitations causing an outflow in the polar cap and whatnot. And so the dynamics are quite a bit more complicated there. But in general, in places where we have data, like North America, we have huge improvement. And even in places where we have no data at all, like the oceans or in the Arctic Ocean, we don't see degradation in performance, and we in fact still see improvement even in the 1 to 2 hour forecast. You do the same thing for swarm, where again, this is close to the F2 peak, and you can see considerable, again, improvement where we have data, and no degradation in places where we don't. And the last thing I wanted to talk about, and I think this was talked about, or Soon talked about this a little bit, is it's important sometimes also to kind of assess these models in terms of their representations on different scales. It's very easily to kind of get a dominant, or your errors be dominated by just kind of fixing the diurnal variability or debiasing the model. And so you can do these quasi-wavelet transforms of the data, so observations, and then from the assimilation system in A-CHAIM, and look at the representation of the model in terms of spatial scales, or different temporal scales, sorry. So this is period in days on the y-axis here, going from 2 days to 30. And you can see the background model, really in these within 10-day timescales, it's not really getting much, obviously. It's an empirical model with a very simple storm time parameterization in it. As you tend to the assimilation system, we recover a lot of that within 10-day variability and some of this, solar rotation timescale variability as well. And here's just a summary of that for Seduncula and Blissville, organized in terms of amplitude of the variability and then period on the y-axis. For E-CHAIM in blue, A-CHAIM in red, and black is the observation. So again, the assimilation system is really helping us in these shorter timescales, which is obviously what we expect. Right, so this is just my concluding remarks. We've produced a high-latitude, near real-time operational data assimilation system. We've conducted some testing with both like measurements and non-like measurements, and over areas where we don't have any data to assimilate, and the system seems to be working fine, which is great. Just to mention that everything that I've plotted up here is openly available. So the source code for E-CHAIM, the background model, is openly available at our website here. And the assimilation, the output from that and tools to interpret that output is openly available as well here. And we have distributions in C, MATLAB, and IDL, so just pick your language. There's a paper now that's currently under review that goes over the data assimilation system. I highly invite you to check out Ben's work. Thank you.
Thank you. Questions?
Very nice work. Some quick question. Are you interested to include this model to CCMC as a community model?
Yeah. So E-CHAIM, I've filled out about half the paperwork for it, but I still have to finish filling the form. It keeps on just kicking the can down the road, unfortunately.
Okay.
I'll get to it eventually. But yes, the intention is to just put it up on the CCMC and let people play with it there as well.
Okay,
Yeah.
that'd be great. Thanks.
Yeah, absolutely.
Okay, let's move on. Thanks, David.
Thank you.
And yeah, next is Piyush, right? Did I pronounce right? Piyush, sorry. Piyush from West Virginia University.
Oh, there's a screen here. Okay. What is forward? This one is forward? Yeah. Oh, okay. All right. No problem. All right. I hope I don't keep you longer than we need to stay here, and hopefully end the session on time. So I'm doing the next two talks. Funnily enough, I shouldn't be doing either of them, but here I am. The first one's going to be a talk. Most of this work, if not all of this work, is done by my student, so he should be really giving this talk. But he's planning to graduate in the fall, so he didn't want to spend time traveling and losing that time that he could be doing to progress his research. So the first talk is titled Scientific Machine Learning, and in this particular case, we are looking at how we could use machine learning to quantify global response of thermosphere density to geomagnetic storms. All right. So the motivation being the desire to better understand how geomagnetic storms affect density, thermospheric density, more so on a global scale. We don't currently, as we know, do a good job at that. There is still a lot of missing information, gaps that need to be filled. And a lot of the work that we've done in the last couple decades has been using satellite measurements, specifically, the satellite accelerometer-derived density measurements from CHAMP, GRACE, GOCHE, and SWARM satellites. And they have provided really good, useful new insights, but they are spatio-temporally limited. So we only always get this information along a satellite trajectory or path. And so the goal here is to see and demonstrate if we can use machine learning to generate a global model using these measurements that can then provide global insights to the response of the thermosphere. And so the data and the model that we use is, where is the thing? It's kind of summarized in this paper down here, but I'm going to quickly kind of do an overview. So we train a neural net, deep neural net model on CHAMP data, CHAMP density data. We call it a CHAMP ML model. The inputs are similar to what most of the models use, but we do end up using a high cadence SIM-H because we did find out that the standard AP or even DST did not give us the best performance because the cadence wasn't high enough. So we ended up using SIM-H as the driver. And the plot on the right essentially shows 4 different models. So the first column is night equator, the second column is day equator, the third column is night pole, and the fourth column is day pole. So basically 4 different spatial locations on the globe. And the top row is the EMSIS model. The second row is the JB 2008 model. Both of them are empirical models. The third row is the HASDM model, or the HASDM ML model that we developed in another one of our papers. And then the fourth is the CHAMP ML model, which is developed in this paper. And both HASDM ML and CHAMP ML model are described in this paper. But what we're trying to show here is that as we drive the model with AP, increasing AP for the first 3 models, and then SIM-H for the last CHAMP ML model, we don't see any response from the top 2 models, EMSIS and JB 2008, that represent any cooling effects due to NO or any other cooling mechanism. Whereas both HASDM and CHAMP ML do show that. So we are also kind of validating our methodology here by saying we are doing something that we are seeing something with our model that we should be seeing. So there's just one small way of validating our model. So for this particular case, again, we're not going to go into any of the scientific inference here. We are just trying to demonstrate that this could be a very good tool to do science with. We do some quantification of density enhancements and depletion, which we call kind of cooling in this case, on the global level. But we're not. This was basically prepared this week, so we're not really doing. We haven't got to a point where we're doing scientific inference, but that's the next step. But so essentially, what we did is we looked at 2 different storms. One, a medium storm. Oh, that's not what I wanted. One, a medium storm going to SIM-H that is about -200, and another, a major storm, which is about -500. And to really concentrate on the drivers, we kind of smoothed out the drivers and kind of took out a lot of these wiggles. So the light black line is the actual variation of SIM-H. The black line is essentially what we end up using, a simplified SIM-H. And then the red line is essentially what we assume as the background or the quiet conditions. So essentially what we are doing is quantifying the enhancement of density over the background, which is the quiet conditions. And we keep them at moderate levels of solar activity. And essentially these 2 storms represent these 2 time periods. December of 2006 is the medium storm, going up to -200 in SIM-H, and then November of 2003 is the really major storm that we're looking at. And we look at, like I said, the density ratio, which is the storm time variation over the quiet background. And so understanding this animation is also will require me to kind of describe exactly what's going on here. So what is being plotted in the animation is the time it takes to reach a given density ratio. Oh, I'm pressing all the wrong buttons, sorry. So the density, I have to go 1 back further and then go, sorry, to start again. So the density ratio that at any snapshot is given up here. And what is being plotted is actually the time it takes for the density to reach that ratio behind the quiet background. And so you can see this is the milder storm. And one more thing to note is that when the region goes white, that means that region never reaches that ratio. So that's kind of explaining what is going on here. But we can see that, as expected, the energy comes in at the high latitudes, gets to a density ratio, a given density ratio very quickly, and then only at the poles do we get density ratios that are larger than 2. as expected. It never really reaches a density ratio of more than 2 at lower latitudes. And the highest density enhancement that we see in this particular case is about 300%. So the next slide, and again, like I said, what we call cooling is really the density depletion or the compression. In certain aspects, we do see cooling as well, where the density ratio density falls below the quiet time. But essentially, we see that for this mild storm, only a small region goes to density ratios that is below 1. So it always falls back. Most of the, on a global scale, falls back down to the quiet time. But on a very small region, it goes back to below the quiet time region. So this is, again, for a milder storm. If we look at the stronger storm, we see density, again, it's plotting the same thing. But here, if you notice, the last time density ratio only went up to about 2.5. Now we are going up to 5. So we do see significantly greater density enhancement, up to about more than 500%. And this is showing kind of what region of the globe on a local time reaches those density ratios. Not everywhere do we see those levels of enhancement. And then on this one, we are going cooling. And here, if you notice, last time for the smaller storm, we went to only about 0.95 on the density ratio. Now we are going down to about 0.8. So this is really, we believe, is a manifestation from a quick look of NO cooling. And only in certain regions as well. So there's probably NO cooling happening globally that takes it to about a density ratio of 0.9, but to 0.8, it only happens in certain parts of the globe. And so this is essentially the full progression to the storm. On the top, you can see as we progress to the different phases of the storm, and then the variation of the density ratio, how the density is varying on a global scale as it progresses through the storm. So again, we wanted to demonstrate this as a potential method to do more scientific investigations. We have not made any scientific inferences right now. But the advantage here is because we are using a neural net model without having any basis functions, we are not really forcing the model to go one way or the other. We are allowing the model to learn the mapping, the global mapping. That's why we call neural networks universal function approximators. It can actually approximate any function. That we are learning straight from the data. There is no background model. There is no basis functions that we are trying to fit the data to. It's purely data-driven. And so hypothetically, we could argue that this is providing us a very realistic picture of what to expect. And so in the future, we could do comparisons with other models, as we've seen throughout the presentations in this session, and possibly even do more scientific studies with the model. So yeah, again, we have not done any scientific inference, but what we presented does have good potential value for science and operations. All of the demonstrations that I showed were at 400-kilometer altitude, which is where we believe the CHAMP ML model is most applicable. We do plan to extend this applicability region based on combining data sets from all these satellites. And lastly, I want to thank NSF for supporting this work through the Career Award. Thank you.
Any questions? I have one question. You say the southern Aurora region is the first, is the first to overcool. But I saw that in the northern Aurora region, seems like it's cooled very, very slow, right? In that next one.
Which one are we talking about? The
next
first storm or the second
next
storm?
Storm 2.
Storm 2.
Yeah, that has it. Yeah. The cool is seems like pretty slow in the northern hemisphere. So my question is pretty simple: why?
Again, we haven't had a chance to break this down. I was talking with Yue earlier, and she was we were trying to decipher it. But like I said, these slides were made 2 days ago. We were just trying to set up the methodology and some demonstrations that we could do. We haven't really had a chance to look at what the inputs are exactly at that time period, or stuff like that. So we will get into that.
Any questions?
But perhaps that could be something part of the asymmetry that we might expect. But that's something we need to look at. Thank you.
Thank you. Okay, moving on. So our next speaker is Dan Weimer, but still presented by Piyush. And
okay, thank you.
Yours.
Yeah, thank you. So like Jack mentioned, this should have been presented by Dan, but he could not make it out. And since I was coming out, he asked me to present this. So this is, I think, work that has been already published in a paper with the same title, I believe. And this is coming out from NASA O2R20 project. And so like I said, this should be, the PI is Dan, and the team's down here. And the basic premise here is we have a new model, or rather Dan has a new model that he's developed with the team, which he calls EXTEMPLAR. There are several different versions that has been developed. We are developing an enhanced machine learning version at the West Virginia University, and I think that's published too. But essentially here, we are comparing it with the recently released SET-HASDM database. And we initially started by calling this as a validation because, as we know, HASDM is the operational standard. But HASDM has its own limitations too, so that's why we kind of decided to change it to not from validation to comparison. So a little bit of background. EXTEMPLAR stands for exospheric temperatures on a polyhedral grid. So essentially, it's an exospheric temperature model. It was first described in this article right here. And the model is based on neutral density measurements from three satellites, CHAMP, GRACE, and SWARM satellites. I think there is one or two maybe SWARM satellites that are used, but so 3 missions, I should say. The background is the EMSIS model. So in this particular case, there is a background model, which is the EMSIS model. And the model basically predicts global mapping of exospheric temperatures, which can then be fed into EMSIS to compute more realistic or more accurate densities. So it's kind of like a feedback scenario. So as we all know, the EMSIS model calculates temperature and density for each species as a function of altitude, and there are 3 parameters it uses to do that. The temperature at the lower boundary, the temperature and its gradient at the lower boundary, the number densities at the lower boundary, and then the exospheric temperature. And so the EXTEMPLAR model, while you can change all of these 3 parameters to achieve the same goal, in this particular case, the EXTEMPLAR model only modifies the exospheric temperature to match the EMSIS model output to the measurements. And as I was saying, given a satellite measurement of neutral density, basically what we are doing is correcting or changing the exospheric temperature in EMSIS such that the density output from EMSIS best matches the density from either of the missions, CHAMP, GRACE, or SWARM. But the point to note that the result still depends on the lower boundary that EMSIS uses, even though we are only modifying the exospheric temperature. And so this is the polyhedral grid that we're talking about. It has about 1,620 cells. And so once, it should be on the next slide. I'm trying to think. Okay. Oh, too much. Okay, so once the exospheric temperatures are estimated for any given density measurement, we take 10 years of data, which spans the CHAMP, GRACE, and SWARM, or 12 years, which spans those mission lives. And then the data is binned into these 620 cells. And then the original EXTEMPLAR model, the linear EXTEMPLAR model, develops a model for exospheric temperature for each of these grid cells. So in reality, there is 1,620 models, each able to predict exospheric temperature in that grid cell. The model is driven by solar indices from SET, the total Poynting vector flux given by the Weimer model, and the integrated temperature delta T value derived from the Poynting flux. And then we also use the solar wind velocity and IMF and not the AP index to drive the Poynting flux model, which gives us some forecasting capability coming from the L1 point to near Earth region. So this is an example showing the exospheric temperatures calculated with the EXTEMPLAR model. On the left is the original grid, the 1620 cells, and on the right is the average or the interpolated one. And these are the inputs for this particular example. And so then, once you have the model predicting the temperatures, you can then feed them into EMSIS model and then predict the densities. And so that's essentially what is shown here, is that when we do that as a feedback loop, the EXTEMPLAR model is able to do a much better job, which is in red compared to the original EMSIS model. So we are able to kind of calibrate. This is one way to calibrate the EMSIS model. And it seems to be working pretty well. And so in this particular case, like I said, although here he calls it a validation study, we are doing comparison of the EXTEMPLAR model with the HASDM model, and we interpolate the HASDM grid, 10 by 15 resolution, to the EXTEMPLAR grid, which is the 1620 cells, to do this comparison. And, one thing I forgot to mention. Yeah, because the grids are different, the way Dan decided to do this is to look at the mean density at a given altitude. And so when you look at these plots, this is the min and the max, but this is the mean density. This is the mean right here. And so when we see on the next plots, these values that are given here are the mean densities at a given altitude. So on the left, going from bottom to top, we have 300 kilometers, 400 kilometers, 600 kilometers, and 800 kilometers. In the black is HASDM, in the red is EXTEMPLAR, and in the blue is EMSIS. So we can see that the HASDM and EXTEMPLAR better match each other, are closer to each other than the EMSIS model. One artifact, I think, is in the next slide. This is, again, I should look here. Log density. Oh, yeah, OK. So these are two different periods, one on the left and one on the right. And then the next slide is essentially comparison over the last solar cycle. So you can see at the X scale, it's 2001 to 2005, or multiple years, at least not the full solar cycle. And again, we see that EXTEMPLAR and HASDM are much closer to each other than EMSIS. And I'm going to skip this in the interest of time, because I just got a notification I have to take my flight as well. But one thing I want to point out is that at 800 kilometers, for some reason, HASDM does not seem to capture the semi-annual variation, even though the background model, which is JB 2008, does. And so that is something that we are still looking into. And then these are just other metrics that he uses to do the comparison. Again, all of these are in the paper that this is representing. And so in the interest of time, I'm just going to reach back to the conclusions and let us know if you have any. Let me know if you have any questions. I'll do my best to answer them.
Thank you. Any question? Yeah.
Yeah, so why is it necessary to convert the data, which is density, to temperature, and then you work on the temperature, and then change it back to density?
I don't, like I said, I don't think it's necessary to do that. I have seen work and papers that do direct calibration of EMSIS. In fact, I have published one of those too. the advantage here is that all of the work by doing this is front-loaded, right? So you can use the EXTEMPLAR model to actually make predictions. Because if you do that using a standard data assimilation scheme, for example, you correct the initial state, assuming you convert it into a dynamic model, but then the evolution in the forecast will still depend on the underlying MSIS model. So this is, we are front-loading all the corrections, and then you have a calibrated model that you can then use to forecast. So this was more directed towards an operational capability. And I'm not denying that there may be other ways to do it, but this is just the one that Dan chose to use.
Okay, thanks.
Thank you.
All right, thank you.
Okay, so last talk in the last section. So I guess I must be very quick. So I'm Jack from CCMC NASA. I'm working on my slide. So this is an international collaboration project that we are going on. So I just want to present some preliminary results of what we are doing. So what's wrong? Oh. Sorry about that. Just as I mentioned, I'm Jack, and I want to thank my colleagues, and Jiayue, Mingyang, and also Sean Brusma, and Eric Sutton, and Henry Liu from NCAR. Next slide, please. Where's my? Okay, it's fine. And so, thank you. The data we use is for here is the neutral density derived from the satellite track. We use the A-CHAIM and Goji, and we use the 6 model, 3 from the empirical model, JB 2008. DTN 2020 is the newest model, and ANSYS 2.0. And we also run a 3 first principle model in-house at CCNC. One is a Gitton version 21.11 and TIEGCM 2, and also the Walk on X version 2.2 is the newest version of the Walk on X. And in theory, that for the empirical model, you can just given any latitude, longitude information into the model, but typically because the empirical model used only 6 or less the degree of the spherical harmonic expansion function. So the typical resolution is about 1,000 kilometers. That is something you must keep in mind. So right now we choose 9 stone time covered from 2001 to 2013. So we want to compare the neutral density from the observation with the model. So I define 4 different phases, and one is a brief stone time. Also, the takeaway from this slide is we use this phase 1 neutral density data to correct all the 6 models, because all the models more or less have some a systematic bias we need to calculate and then correct that. And we use these corrections model output to calculate how these models performance during the stone time. So we calculate 4 different metrics here: mean ratio, standard deviation, and peak amplitude and lag time. The takeaway for this slide is that we calculate in the log space, not just in the linear space. So this is a scale factor we calculate during the phase 1. So you see the value larger than 1 means the model is underestimate, yeah. No, sorry, yeah, underestimate, yeah. And so for the value less than 1 means the model overestimate. So for Keaton is the only one underestimating the neutral density, and yeah, in general. So this is the mean ratio we have. So you could see Keaton has a very large deviation compared with the phi model, but I would not say this is performs worse than others, but yeah. So yeah. And this is standard deviation we have. The standard deviation represents a combination of the ability for the model to reproduce the observed density variations and the geophysical noise. So you could see one thing I need to mention that I use the different y-axis scale for the Keaton because Keaton, at least in the 9 cases, is performed much worse than other models. So typically, you can see during the storm time, the phase 2 and the phase 3, sorry. And you can see this standard deviation rise pretty significantly compared with the pre-storm time and the phase 4 time. And this one is a relative peak amplitude, which means that so we compare with the largest amplitude we observe with the model predict. So pretty interesting things like the Keaton can predict the peak amplitude better than other models. And also you can see the lag time for the greater than 0 means that the model predict the peak amplitude happen in the later time. Since again, the Keaton is performing better than the other models in our simulations. So that's all I have, and I want to, in the last slide, I want to advertise our ongoing project in the ISWA. So if you're interested in the neutral density validation, please visit the website and consider to join us. Thank you. Any questions? No, I guess no. Oh, thank you so much for everyone to stay so long for here. So I want you join me to thank our all speakers again. And thank you. I will conclude our section here. Thanks.